This episode is called Low-Cost Indoor Air Quality Sensors by Dr. Jordan Clark of The Ohio State University, who spoke at the NAFA Technical Seminar in Louisville, Kentucky in April 2022. Enjoy.
You're listening to the Talking Air Filtration podcast, where you get to know the people that make air filtration possible and help us all breathe easier. Because clean air matters.
We'll get insights from air filtration professionals and learn how they became successful in their careers. Along the way, we will discuss best practices, guidelines, trends, and challenges in air filtration in a variety of applications. We hope HVAC, air filtration, and indoor air quality pros, including business development, engineering, building owners, and facilities management, will enjoy the insights our guests will bring to this podcast.
Our final speaker for today is Dr. Jordan Clark. Dr. Clark is a building scientist and assistant professor at The Ohio State University. Dr. Clark research is concerned with reducing energy use and carbon emissions attributed to indoor environmental control. He is a recognized leader in the area of indoor air quality, sensing and data-driven controls in an indoor environment. We are looking forward to what he has to say on low-cost indoor air sensors. Dr. Clark.
Hi, everybody. Thanks for the opportunity to talk about indoor air quality sensors today. Any Buckeyes in the room? That's what I'm talking about, OH. So first of all, quick acknowledgement to the people who funded the research I'm going to talk about today. This is mostly funded by ASHVE under RP 1756. And then we've extended that a little bit with some funding from National Science Foundation. And then we're just getting started on this U.S. Department of Energy Connected Communities project, where we're going to extend some of this work as well. So let's talk about the way we control air quality in buildings. And by control, I mean the engineering controls that were talked about earlier. Continuous control, what do we do? I think we all are quite aware that the two ways we control air quality in buildings are through prescribed ventilation rates, right? And prescribed filtration effectiveness. That means no real-time feedback from the building, with the one exception being some CO2 signals that might come back for DCV systems. This occurs in fewer than 10% of the buildings in the United States, and we don't even have a performance-based metric that's widely used. We have the IAQ procedure in 62.1, but I'm told this is fewer than 1% of buildings are controlled with that IAQ procedure. So for the most part, we're dumping in quantities of air, nothing to do with the quality of air, and we're prescribing filter effectiveness, right? When I first learned this as a student, and when my students learn this now, they're kind of shocked, right? We got a bunch of smart scientists and engineers who are working on this, and the best we can do is prescribe quantities of air, dump them in, and kind of pray for the best. So just think, what would happen if we did our thermal control in this way, right? What if we dumped in a certain quantity of air at a certain temperature and said, let's just wait for the occupants to complain, and that's the only kind of feedback that we have. Take out all the thermostats, we wouldn't have very good buildings. But this is the state of IAQ control in most of our buildings. And at the same time, we're paying a lot of money for this and using a lot of energy for this. So commercial buildings, about 10% of our energy consumed in commercial buildings goes directly to ventilation. This comes out to about 1.5% of all energy consumed in the United States is for ventilation of commercial buildings. So it's across sectors, across transportation, industry, agriculture, everything. About 1.5% of all of our energy is used to ventilate buildings. Another 2% of all energy use in the United States is attributable to leaks in our residences, so our accidental ventilation of our homes. And then, of course, this crowd knows that fan power used to push air through our filters is a non-trivial contributor to energy consumption as well. I don't have a good number for that, and the EIA does not publish that, but we know that that's non-trivial. And becoming a bigger issue every day is not just the energy that's consumed, but the effect on peak power demand. So we're worried about our aging electrical infrastructure, and specifically we're worried about a peak power demand, that those grid peak times in the late afternoon. Everybody's turning on their air conditioners. All of the commercial buildings are still running, and we have to size everything accordingly. About 10%, this is work that we've done, about 10% of all those grid peaks is attributable, this is the power demand, not the energy, is attributable to ventilation of buildings, right? It's not too hard to believe. If you think about it, the late afternoon, everything's really high enthalpy outside. We're bringing in all this hot, humid air. We need to condition all this. 10% of all peak power demand. So we're paying quite a bit of energy. And this is what results. This is a graph from 1999. This is an ASHVE journal article showing the evolution of the prescribed rates within standard 62 and how they've changed over the years. So we had some initial kind of guesses at what we needed. And then late 19th century, this is kind of the hygiene revolution and germ theory is developed and things. So we thought we should really get a lot of air into our buildings. This is back when everything was kind of naturally ventilated. So we didn't have to worry about paying for it too much. And then middle of the 20th century, central air conditioning, central heating becomes more widely adopted. We realize we have to pay for it, and you see the rates plummet. Beginning of the 80s, we have an energy crisis, and rates go down further, right? And then, of course, everybody knows what happens in the 80s. We get this rash of sick building syndrome symptoms, and then we shoot our rates back up to about where we are now on the right-hand side. This has changed the way we prescribe things, of course. This is all based on per person rates. For all of that time, now we prescribe things based on per person and per floor area, but we're right about the same. This is for an office building. And you see this wild oscillation and how these things have changed over the years. Where are we going from here? What are these prescribed rates going to be in the future? We're just coming out of COVID. We also have what's looking like a permanent wildfire season on the West Coast. It's kind of on everybody's mind. There's a lot of talk about how do we, take this moment to make a bit of a revolution in our buildings. A lot of wild numbers being thrown around. One number that's being thrown around a lot is this 10 liters per second. That would put us right about there on this chart. You can think about the energy consequences for that and the power demand consequences for that. There'll be a big step up. Some people are talking about treating buildings more like we treat hospitals to reduce, transmission of viruses. You guys know the air change rates in hospitals can be 6, 12, 18 air changes per hour. So it's an enormous increase in the amount of air that we'd be bringing in to buildings if we were to treat them like hospitals. At the same time, if you go on the EPA website right now and you look at their guidance for what to do during wildfires, and again, this is a 3 or 4 month season on the West Coast, they actually say if you have a central HVAC system, this is talking about in your home, that has dedicated ventilation to actually shut the damper so that you're not bringing in any ventilation air at all. That's lower bound on recommendations is about 0, and upper bound is something like 16 air changes per hour. So we got a wide range of what might happen going forward. So prescribed filtration effectiveness, a little bit more calm, not as many oscillations in there, but this is about how they've evolved over the years. I'm showing 62.2, that is that bottom black line, 62.1 in the PM 2.5 attainment areas and PM and 62.1 in the PM 2.5 non-attainment areas. So this is for outdoor air. Prescribed MERV ratings for each of those situations. And on the right-hand side, I'm showing dashed lines. If you guys were involved in ASHVE for the last 3 years, a lot of people were talking about prescribing MERV 13 across the board. That didn't happen in either one of the standards, but there's reason to think that it might very well happen for the 2025 edition. And also, we know if you've been in the room there, that whether the changes happen is often a function of, who happens to be in the room voting that day. There's science that goes into it for sure, but there's a lot of politics as well. So the point of showing these last 2 slides is to suggest that we may be due for some, total rethinking about the way we do these, especially on the ventilation rates. Like I said, when I saw that, it's like, this almost looks like trial and error over the last 50 years, right? We jack them up. It's too much energy. We turn them down. People aren't healthy and they complain. We turn them back up. Maybe we need a different paradigm completely. One suggestion for the new paradigm, if you guys seen the movie Moneyball, so I got a baseball and a movie reference as well. If you haven't, earmuffs, because I'm going to ruin it for you. The basic story is that the baseball team's struggling a little bit. Brad Pitt wants to kind of revolutionize how they do things. He brings in this geeky guy with a bunch of numbers, and they use data to make decisions on who to hire, who to play, etc. And they transform the way the baseball team is run from this kind of prescribed, old way of doing things to this data-driven framework. They beat everybody in the league, and then supposedly everybody kind of adopts that way of doing things. So this data-driven paradigm is taking over everything, right? So self-driving cars, stock trading, medicine, and of course it's taking over our buildings as well, mostly on the energy side. So this is the U.S. Department of Energy depiction of a grid interactive efficient building. So you can see the main feature of these grid interactive efficient buildings of the future is ubiquitous sensing, right? So sensing not only things that we're used to like occupancy, but also things like the state of lighting, the state of our windows, nearby distributed energy resources, So state of batteries, EV charging stations nearby, photovoltaics, and also taking signals from the electrical grid and knowing what the grid needs at that time, how the grid's operating, throwing everything into a centralized platform and being able to make better decisions the same way the baseball team did based on all this data that's coming in. And this is the kind of direction we're moving. You'll notice up here that there's no mention of indoor air quality. And that's something that I'm trying to do, is to get DOE eventually. Over the course of the next 5 years, we'll be working on this sort of thing on the Ohio State campus. I'm going to try to get them to stick a bubble for air quality on there as well. So the first step in getting the data that we need to move towards this data-driven approach to our air quality control is, of course, the hardware that's going to give us that data. So we're talking about measuring in real time the actual variables that we care about in buildings. So instead of prescribing just how much air gets in, we can actually measure the quality in real time. This has been the kind of bottleneck up until right about now, and I'll talk about the state of the art where that actually is today. So many of these sensors, air quality sensors, airborne pollutant sensors, are coming on the market, and I actually hear about a new one every 2 or 3 months now. Somebody alerts me to this. Some of you might have some of these in your home. A lot of people were buying these, and they're actually selling out during the pandemic. Everybody kind of wanted to be aware of what's going on in their home. These can range from something on the left. I'm showing like these bare sensors. These are the DIY sensors that you have to use some kind of Arduino or some kind of interface to actually get information out of, all the way up to more expensive devices that are packaged, maybe packaged with multiple sensors, and they have some kind of graphical user interface that you can interact with on the web. They may have some other features on the sensor themselves where you can cycle through, etc. So I'm going to talk today mainly about the low-cost particle sensors that are available. These are consumer products, and I'm defining low cost right now as less than $1,000. There's several different definitions for low cost out there. One thing to note is that most of these packaged consumer devices, the price point that the best of them, let's say, are falling into is about $250. So that's the kind of price point we're talking about. The sensors themselves, the bare sensors that might be integrated into like a standalone air cleaner or something like that, those can be purchased for as little as $6. More common is something around the $25 price point. So that's the kind of devices I'm going to be talking about. And how do they work? So the first thing is we have some kind of housing that separates the interior of the sensor from the outside of the sensor. This may seem kind of obvious, but this turns out to be a bit of an issue in the performance. What the housing is made of actually makes a difference. A lot of the first versions were just die-cast plastic. Some of the better performing versions are aluminum housing, so a little bit more expensive, but there's a reason for that I'll go through in a second. About 2 or 3 inches on the side. They have some means of conveying air through the sensor. So again, this ends up being important. Some of the first versions of these had just resistors dissipating heat, and they moved air through with a buoyant current. Those didn't really work very well. So most of them, almost all of them, I think now, have one or more fans that are moving air through that little sensor. Then some kind of LED light source. Virtually all of these low-cost particle sensors that are on the market, I think all of them indeed, are optical sensors, meaning there's some kind of light source, in this case just an LED, that we shine on this stream of air. And the principle that makes it all work is that some of that light bounces off the particles to the other side, maybe magnified with one or more lenses, and then it's received by a photoreceptor on the other side. And from that signal, what the photoreceptor receives, we can back out some information about the concentration of the particles in that stream in a very cheap way, right? Inexpensive components. And then this is output as an electrical signal, and the end user or the original manufacturer can do some post-processing with that electrical signal to kind of improve it, do some calibration, combine it with other information like maybe humidity in the ambient air to correct for things. And that's the basic functionality of these low-cost particle sensors I'm going to talk about. So these are some of the guts of some of the commercially available sensors. It's kind of 4 different sensors, and you can see how that shakes out in these sensors. So like I said, these are either sold as bare sensors. There's 2 examples of the bare sensors on the left, or as packaged device. The packaged devices will have some kind of housing. The housing kind of depend on the intended application. So the one on the top right there is actually intended to be worn on a lanyard around your neck, or even like attached to a bicycle or something. This company had the vision of mapping out air quality with this citizen science stuff. The one on the right is usually, the bottom right is usually a stationary sensor that you put on a pole, kind of with the sensors, the open part facing down. And there's another popular device that looks quite a bit like that. The one in the middle here actually has several sensors packaged in there. I think a couple gas sensors and a relative humidity, if I'm not mistaken. So this is the kind of things that we're talking about. We've done a lot of performance testing in Ohio State on these things to just get an idea of what the issues were with these. What are these things capable of? What do we need to watch out for? How valid are some of the claims that are being made about how well these things can perform? I've done most of this testing with my colleague, Andy May, Dr. Andy May at Ohio State. He's done a lot of this testing with me. We did field testing. So we had this little test house at Ohio State, and we have a couple of naturally occurring particle sources nearby. So there's a gravel road nearby that kicks up a lot of dust. And there's also a big highway about 100 yards away that's pretty heavily trafficked. So we have some naturally occurring particle sources, and then we created some of our own. So we did things like cooking or lighting incense on fire, lighting some candles, burning some toast, etc., cleaning. And we subjected these sensors to all these different particle sources, and we also co-located much more expensive devices to kind of see how they compared to those more expensive kind of research-grade devices.
Are your air filtration personnel NAFA certified? Ask if they belong to NAFA and have their certified air filter specialist or NAFA certified technician designations. The CAFS and NCT designations are earned after rigorous exams and demonstrate that the air filtration professional has a high degree of knowledge and professionalism. To learn more about NAFA certifications, visit nafahq.org.
We also did lab testing where we had a better control in the environment that these were being tested in, so we can control the relative humidity, control the temperature, etc. I had this little controlled environment chamber on the bottom right there that can precisely control temperature and relative humidity, but I didn't want to get it dirty, so we actually siphoned air out of that, put it in this makeshift insulation box there, and put our sensors in there, and then put all the dirty stuff in there and subject them to that. So we did this for about 2 years, and then we continued some analysis after that. So we've actually been at this for about 3 years. These are a couple of the students who worked on it. That's their dog crate from Walmart that we filled with these sensors. And you could see them kind of running around Ohio State campus for a couple of years testing these. So we subjected these to a bunch of different tests to see how they performed. The first test, this is in the field studies. The first thing we wanted to know was if we just have an event, can the sensors register that event, and can they come back to their baseline concentration after the event's over? There was some initial evidence in the literature that many of the sensors, these consumer products, actually couldn't do that. They would get stuck at the high concentration and would never come back. We didn't see any of that. We saw for all the 8 sensors that we tested that they were all able to register an event. So if all you cared about was activating some device or something in response to a particle emission event, it seems like these low-cost sensors are very capable of doing that. On the right-hand side, we're showing basically the integral under each of these. I was told not to get too technical, but throw out the word integral. Basically, if we want to know something about the exposure during these events of the people, what the actual concentrations were throughout that event, we can compare what they were with the low-cost sensors to what they were with the higher-cost reference instrument. That's what we're showing on the right. So a perfect sensor would have an integral of about 1. This is the relative exposure. You can see there's a wide range based on the source type and on the device itself in this. So if we want to actually quantitative understanding of exposure during these events, maybe there's a lot more variation in performance for these sensors. Next thing we noticed in the field was that there's a huge effective averaging time. So we wanted to understand how quickly we can maybe make a decision based on signals from these sensors. There's been some work before us suggesting different averaging times. Consensus is longer averaging times, the better apparent performance. We showed that at about an hour, these graphs are showing the same thing. At about an hour, the apparent performance drops off. We're showing the R-squared, the correlation to the research grade instruments in each of these. So a perfect sensor would be up at 1 the whole time. And then we're showing averaging time on the x-axis. Basically, the takeaway from this is that at time scales less than an hour, something is happening. We think it might be like spatial averaging. So things are moving around, the air's moving around, and it needs to be kind of averaged out in order to get a reading that's comparable to the reference grade instrument. Basically, at time scales less than an hour, the performance seems to drop off quite a bit. Intermodel consistency. So by this, we mean this is showing someone else's work from 2013. One of the first explorations of the performance of these devices showed that even with the same make and model, if you put 2 instances or 10 instances of the same sensor right next to each other, they gave wildly different results, which is what you're seeing here. So this is dust concentration, micrograms per cubic meter. And these are all co-located, and they're the same make and model, just different instances, and they're giving about an order of magnitude difference in output. So we wanted to look at the 8 different ones that we tested and see if that was the case with these things. What we found was there's wide variation in the performance of these consumer devices. 5 of the models that we tested had very good correlation, at least, to each other. So that's something that could be kind of tweaked with calibration. At least they're correlated to each other's signals. 2 of the models, and I swear we tested 8, so I don't know where the 8th one went, but 2 of the models actually weren't even correlated to each other. So 2 instances of the same sensor, same make, same model, located in the same place, and then one was going up and one was going down, things like that. So the not so good ones are really not so good, is the takeaway from that. Next thing we noticed is that there's a very distinct, what I'm calling the functional range. So this is the concentrations that can be measured. On the high end, if you get a great enough concentration, we get this nonlinearity, which means if you, depending on where you are, what concentration you're at, you're going to get totally different apparent performance. At the low end of the scale, we get a lot of noise. So the signal from the sensor is kind of overwhelmed by the noise in the sensor, and we can't really make much sense of what's going on. So in between that, those 2 extremes is what we're calling the functional range. And we found that each of these sensors has a very distinct functional range. So on the lower end, I'm showing 2 examples of the performance of the sensors here. The good sensor, what we're calling the good sensor, if you look at the blue dots, like a perfect sensor again would have blue dots all along the top there at 1, perfect correlation to the reference instrument. Anyway, I'm showing this as a function of the concentration that they're measuring. So a perfect sensor would have it at the top for the entire range that we had 1. And you can see that the performance starts to drop off here at about 4 micrograms per cubic meter. So it's pretty clean air. So it's pretty good performance. Whereas the one on the right starts to drop off substantially as high as about 60 micrograms per cubic meter. So if we wanted to use it, in our homes to get some continuous understanding of exposure or something like that, that's probably not something that we'd want to use, but maybe it's applicable in some industrial setting or something like that. So this is the kind of summary of this lower limits of quantification. Most of the ones that we tested did pretty well, down to about 4 or 5 micrograms per cubic meter. It's dependent on the source that they were measuring. A couple of the ones that we tested started to drop off as high as, I'm showing about 18 micrograms per cubic meter there. So again, wide variety in the performance of these consumer devices. I won't go too deep into this, but basically one thing we look at for any sensor is the linearity, meaning no matter where you are, what you're sensing, in this case concentration, you're gonna have the same kind of response of the sensor all along that range. So on the right-hand side, we do have that linearity up to something like 2,000 micrograms per cubic meter. Great. On the left-hand side is showing not as good of a sensor, where it's almost never linear behavior, and it's really hard to make sense of the data coming out of the sensor. So again, wide variety in performance. Another issue is how these things perform when subjected to different sources. So you can imagine we're going to leave one of these in a building. It's going to see a lot of different things over its lifetime. We would like it to perform the same for all the different sources it's going to see. I'm showing 3 different behaviors here. The right-hand graphs are all magnifications of the left-hand graph, so it's the same data for 3 different sensors. So each row is a different sensor we tested. If you look at the top right graph, all those different colors represent a different source that it's being subjected to. So we did like incense, burnt toast, a humidifier, some deodorizing spray, some cooking, etc. And we see that, again, a perfect sensor, all those dots would fall on that black line. That's like a 1-to-1 line. The x-axis is the reference instrument. The y-axis is the low-cost instrument. For the one on the top right, that's a pretty good sensor. A lot of the different sources are falling really close to that black line. And then a couple of them, both of those sources, the green and the yellow, these are kind of water sources. So it's water vapor from cooking. And then I think a deodorizing spray. That didn't perform very well for those. But for the rest of them, we had pretty consistent performance. In the middle, we're showing a lot of linear response. So that's what we wanted, except the slope of the lines are all different based on which source it's actually measuring. So that kind of suggests you need a different calibration for each thing that it's going to see, which is probably not so feasible. If you knew exactly what it's going to be measuring over the course of its lifetime, you may be able to deal with that. If not, you're going to get different performance for different types of particles. And on the bottom right, that's a sensor that just didn't work very well for any of them. Effects of temperature. So we showed and other people showed that these are relatively insensitive to temperature, at least in the ranges that we would see in buildings. We went up to like 40 degrees Celsius, so even outside of our buildings. There was originally thought that there might be a temperature effect. There was some evidence of that in the literature. Turns out that's most likely a light effect. So these are optical sensors. So if you're baking them with the sun, they're going to get hot, but that's not really what's driving the deviation in performance. It's actually some radiation that's getting through the housing of that sensor and messing with the optical sensor. So we think they're relatively insensitive to temperature, or at least there's no evidence they are sensitive to temperature. Relative humidity is a totally different story, right? We and others have shown that there's quite a bit of sensitivity to relative humidity. This is showing the same sensor subjected to the same kind of particles at 4 different relative humidities. So we're seeing 4 totally different responses on that graph, depending on what the humidity is. And the mechanisms for that have even been articulated in the literature. There's 4 or 5 different things that might cause that to happen there. So the takeaway from that is basically that this is an effect that can be post-processed out again. So takeaway from this is kind of, if you're in the market for one of these sensors, maybe you want to buy one of the products that has a relative humidity sensor nearby and uses both of those pieces of information to improve the accuracy of that. Size effects, this is what most people kind of think about when they think about particles and the different behavior of particles, is what the size is, and indeed that matters quite a bit. This is someone else's work on the right-hand side that's showing let's call it the performance as a function of size. You can see we get the very distinct peak there. That's at about 2.5 microns. We almost certainly this is because of the calibration. So these things are calibrated for a certain size of particle, and we see that the performance deviates wildly if you're subjecting them to a different size particle. A couple interesting things from our work. We showed that the correlation to the reference instrument and the slope of that response, which should be 1 in a perfect sensor again, did not drop very sharply at the very small particles. We were expecting it to almost not be able to see them at all. And we showed that it wasn't perfect for sure. That line is showing the R squared, and the box and whiskers are showing the slope of the line. So this should be about 1 in a perfect sensor, as should the line on the right axis. We are still getting a response. We got a slope of about 50 or 60%. So there is some hope that these could even detect particles as small as 200 or 300 nanometers. Composition, there seems to be a bit of an effect of not just the size. So if you subject them to a different source, obviously the particles from that source are going to have a different size distribution, but they're also going to be made of different stuff, right? So there seems to be a bit of an independent effect of the composition of the particles. And you can imagine how that might happen if we have some light-colored particles as opposed to dark-colored particles. They're going to interact with the optical signal differently, independent of their size. So just some things to think about when we're deploying these. There's some kind of conflicting evidence about drift. So everybody wants to know, how long are these going to last in our environments? How often do we have to calibrate them or change them out? And there's estimates from a few months to a few years in the literature. We're going to get a better wrap on this over the next 5 years. We're going to deploy a lot of these in high-estate buildings, and we should get a much better understanding of frequency of calibration or frequency of replacement. Yeah, that's all I'll say about that. Predictive ability. So we're just starting to mess around with being able to predict what the concentrations are going to be in the future based on a history of the concentrations that we measured from the signals. You can imagine what we could do with that. So if we know like a high concentration event is about to happen, we can activate some cleaning device or, close the ventilation system for a second, et cetera, and improve our indoor air quality substantially that way. So we've been using machine learning along with the data from these sensors to see a few things. One, can we predict when these high concentration events are going to happen? And 2, can we predict a time series of the concentrations so we can kind of optimize control? We did a pilot study. This is very preliminary, but we're encouraged by this. In the pilot study for the best of these algorithms that we used, we predicted 98% of the event data correctly, meaning either was an event or it wasn't, and 98% of the time, our prediction for 1 hour ahead was correct for that. So encouraging. We're going to do a lot more work like this moving forward. We also predicted 86% of the variance in the time series data, so our model performed relatively well. This is a small data set and a small number of events, but we're beefing this up, like I said, over the next 5 years. So the big takeaways from this low-cost particle sensor research, this is about the most, let's say, the strongest statement I can make, and it's got a whole bunch of caveats in it about the state of the art of low-cost particle sensors. It says that the best performing low-cost particle sensors, and this is very much not true of the worst performing low-cost particle sensors, and not even the average, but the best performing of these can perform close to their much more expensive counterparts when they're used under the conditions that they're intended for, right? So when they're used under the relative humidity and under the concentration range and for the types of particles that they're expected to be used for. If they're not exactly used in those conditions that they're calibrated for, you can do a lot in post-processing with information from, for example, a relative humidity sensor nearby. Averaging time matters a lot. That's one of the big takeaways. So if we were going to control buildings, probably about an hour is about the best we could do right now. A lot more information if anybody doesn't think this was geeky enough and you want to go even deeper into it. We got 4 publications on that. So I'm going to very briefly talk about gas sensors just to be complete. Most of the work we've done is on particle sensors. I'm kind of reviewing a few friends' work on gas sensors. First of all, let's talk about TVOCs. I think most people in this room know this, but perhaps not. I'm talking to a lot of people. There's actually consulting companies that are offering this as a service where they're putting these low-cost sensors in buildings and telling clients things about how their building is performing, et cetera. And what I'm hearing is that everybody wants to know their VOC concentrations and ascribes a lot of value to that VOC signal. I think a lot of us know that VOC signal has some problems with it. The first problem is that this total VOCs is not almost ever what the TVOC sensors measure, right? Any TVOC sensor is going to either measure a subset of VOCs or it's going to be more sensitive to certain VOCs and less to another. So we're almost never getting TVOCs from our TVOC sensor. And the second problem, which is probably the bigger problem, is that it's not clear that even if that's what we were getting, that would be of any value, right? And what I mean by that is, say our VOC sensor told us that we had something like 100 parts per million, right? 100 ppm TVOCs. If the 100 ppm were measuring all ethanol, which is very possible in an indoor environment, it's a commonly found VOC, we would be well under OSHA and NIOSH recommended ranges for 8 hours. We could be exposed to that 100 ppm for a long time. If, on the other hand, it were measuring all formaldehyde, which is another common VOC in indoor environments, we would be a couple orders of magnitude above what we're supposed to be hanging out at. And would be several orders of magnitude over the lowest prescribed 16 ppb threshold. So the point of this is because of the lack of specificity of the TVOC, we don't know which VOC we're measuring. That signal doesn't do much for us. A lot of lay people and even educated people think that this is something, we could actionable information that we can do something with. I think that's probably not the case. That's the takeaway from this. So almost all these consumer devices, if they have multiple sensors, are going to have a VOC sensor in it. And the recommendation is to kind of ignore any information from that. What we could do instead is to measure individual gases, but that gets quite tricky. So this is showing the example of as close as we have to a low-cost formaldehyde sensor. So this is specifically targeting formaldehyde. And the way this does this is by a color change that happens in this material in the presence of formaldehyde. So the color of that little film changes in proportion to the concentration of formaldehyde nearby. And then we, again, bounce a little light off of it. The reflectance of the film changes as the color changes. And then what bounces off, we can back out something about the concentration of formaldehyde. So this was the consensus best formaldehyde monitor for a long time. I'm not a formaldehyde expert, but I talked to several colleagues who are, and they were all in agreement that was the best of the performance of this at LBNL, Lawrence Berkeley Lab. Outcome was that, again, at long time scales, these did pretty well. They were comparable to the passive sampler that they took as their kind of ground truth. At shorter time scales that we kind of like to control buildings with, like 30 minutes, the correlation was relatively poor. We had an R-squared of 0.33 and a 0.66. And as they moved to lower concentrations, the concentrations that were likely to find in indoor environments, the performance got even worse. So even the consensus best monitor is kind of mixed reviews. And I'm told by the vendor a couple months ago that this has actually been discontinued. So this is the best monitor on the market. There's not enough market for it, and it's been discontinued. So I don't know exactly where we are as far as formaldehyde sensing. So gas sensing has a long way to go. We also tried a few signals of these VOC sensors and these formaldehyde sensors in terms of their predictive ability with that machine learning that I was talking about, and we didn't have very good luck on that as well. So that's the upshot on the gases. The particles sensors seem to be approaching viability as long as they're used within their domain of applicability. These non-specific TVOC sensors probably aren't so useful. Seems like formaldehyde is getting there, but it needs some more time. And I just wanted to make you aware of a couple different standardization efforts. There is a standardization effort at ASTM that's looking at how we test these things, like analogous to 52.2, but instead of filters, these low-cost sensors. And we've just formed a working group under 62.1 to be able to allow control based on these sensors eventually. So that's kind of the state of the art with low-cost IAQ sensors, and I'm happy to answer any questions.
Thanks so much, Jordan. When you were looking at those low-cost sensors, were you able to identify inside those sensors if they, like the Bear sensor, were they all different from different manufacturers?
That's a good question. You mean the integrated devices, the packaged devices, are they using different sensors? They are kind of converging on one particular sensor. So I don't want to stand up and say which one it is, but I can whisper it to you later if you want to know. But yeah, the best performing consumer devices all happen to have one particular sensor. It's the one with the aluminum housing, has a couple fans.
Okay, thank you.
Hey, Jordan, you were saying that the particle sensors are the ones that are closest to really being ready for prime time. What is the one application for the particle sensors that you really think is that kick-butt application that's really ready to go where we could use it the best?
Good question. So there are a couple different instances of smart range hoods being developed right now. I don't know if there's any actually commercially available, but I know Brown and a few other people are making smart range hoods. So that's an obvious first application. Another thing would be things like people are actually doing this. It turns out I proposed this to 62.1 that would create an addendum that would allow for this, but it turns out design engineers are actually doing this already and kind of getting around the standard a little bit. If you have a truck idling in a loading dock, for example, and you have an intake nearby, you're just pulling in all that diesel exhaust. So that's an obvious application. You could put a particle sensor on that intake and temporarily shut the dampers, and then when the truck leaves, open it back up. So those are probably the two, simplest. Also, any kind of registering any kind of event in a place where you have a lot of cooking, for example, and bumping up ventilation temporarily, that would be an obvious application for this.
Okay, there's been some discussion about having CO2 and particles displayed, like in a room like this, where they'd actually be up on the wall. They're doing something like this in Japan for theaters. How far away are we from doing something like that?
In terms of the technology, or in terms of, the desire to do so, or
The technology part of it.
I don't think there's anything standing in the way of doing that right now as far as the technology. Whether people are willing to do that and show everybody their secrets, how their environments are, that's a different story.
Well, the advantage would be that you could, people would look at it and they say the CO2 is 1,300. The people in the hotel would modify the CO2 very quickly if people knew what the problem was and there was no ventilation.
Absolutely.
Good.
Thank you.
Thanks for listening to the Talking Air Filtration podcast, a production of the National Air Filtration Association. Clean air matters.